Okay, we should get started. I have two other things I would like to do. I would like to talk about this very important phenomenon, which is how expensive should my heuristic be? It is actually an important question that we need to answer. So, in this graph, this is not a real graph drawn by empirical data, but this is intuitive graph. So, on the y axis we have the cost of computing the solution. So, it is running time, let us say, it is basically running time, okay. And I am showing you two graphs, and what I am varying on the x axis is how informative the heuristic is. So, most informative heuristic is the, as we have discussed, H star heuristic, and most uninformative heuristic is the H 0 heuristic. So, what is H star? I know the exact optimal solution cost, and what is H 0? I know nothing, I feel I am the goal, right. And so, ideally what will happen is that the cost of computing the heuristic is going to increase, obviously, because here I have to do no work whatsoever. I would say every heuristic is 0, that is 0 work, and so I will not spend any time in actually doing the computation. If I have to do H 1, then I have to at least count the number of misplaced tiles. If I have to do H 2, then not only do I have to count the number of misplaced tiles, I also have to add the distances and figure out and add them, a little bit more work, not too much, of course. Like in the previous example, if I have to do shortest path, then it is one kind of an algorithm. If I have to do minimum spanning tree, then it is a different kind of an algorithm. I may end up doing something even better, that it might be even more expensive algorithm. So, what is happening is that as I increase the informativeness of the heuristic, the cost to compute the heuristic increases, and you can sort of assume that it increases somewhat exponentially, because eventually the problems that we are solving are NP hard at least, and therefore, in practice they will be more exponential, at least today. So, this cost is going to go up very fast. On the other hand, if I give you a good heuristic, your cost of searching is going to reduce. We just discussed that A star with H 1 took 39,000 expansions, where A star with H 2 took only 1600. So, therefore, the cost of actually searching is going to reduce, and then you have to ask the question, well, what is the right heuristic to compute? And in fact, the total cost that you will finally incur is going to be something like this. This will be the total cost, because in total cost you also have to do heuristic computation, plus you also have to do search. And so, it feels like, right, it feels like the right point, the right amount of heuristic computation is something like this. Of course, this graph is never given to you. You have to use some intuition, but this is an important intuition, that terrible heuristic is terrible, but really good heuristic is also terrible. The really good heuristic is terrible because you will spend a lot of time computing it, even if you end up spending no time searching with it, and vice versa. So, therefore, but the question is, where does this minimum occur? And researchers have sort of asked this question sometimes, and sort of the conventional wisdom was that the global minimum is close to cheaper heuristics. In practice, you always want your heuristic to be polynomially computable, because if the heuristic itself is exponentially computable, then it is a much more expensive algorithm. But even with polynomial algorithm, what this is saying, that the conventional wisdom is that not only should it be polynomial, it should be lower order polynomial, it may be linear, at worst quadratic. Almost never do we use big time algorithms for heuristic computations in practice. But there are some new insights that have come out in the last 10-15 years, which have made people question this conventional wisdom, and in fact, people have found that cheaper heuristics may not always be the best idea. Sometimes somewhat more expensive heuristics may be a better idea, and the examples there is pattern databases that we will study and plan graph heuristics that we will not study. Planning graph heuristics are actually very important set of heuristics for planning problems. I wish we could discuss this. It is an area I did my PhD in, so it is close to my heart, but we will not talk about it. But I will briefly talk about pattern database heuristics because it is an easy thing to learn and it gives you a lot of value. So, let us quickly talk about pattern database heuristics. So, let us say, so and some of these slides have been taken by Richard Koff, who is now very senior, but also extremely well known and famous researcher in the field of search. He was at UCLA, or he still is probably at UCLA. And so, he says that look, this is the size of search space if I am doing brute force search, right. Of course, we do not want to do brute force search, but just for completeness. 8 puzzle is only 10 to the power 5 nodes anyway. So, it should be completed in about 0.01 seconds. Now, take these numbers with a grain of salt because these are older slides, 10-15-year-old slides. So, numbers would have changed a little bit, but when we are talking about 2 billion years, it is possible that the numbers have changed, but they have gone to 2 million years. So, we do not care, it is still equally bad, right. We can't do this. So, 8 puzzle 0.01 seconds, Rubik's cube 2 by 2 Rubik's cube, 2 by 2 by 2, 0.2 seconds, 3 by 3 by 3 Rubik's cube. If you do not give me any information, if you do not give me an admissible heuristic or any heuristic, 68,000 years. That is why Rubik's cube is supposed to be a difficult problem, at least, right. 24 puzzle, just an extension of 8 puzzle to 5 cross 5, 12 billion years. Of course, you would say who cares for brute force, let us talk about IDA star with some heuristics. So, here is performance of IDA star on 15 puzzle, random 15 puzzle instances solved by IDA star using Manhattan distance heuristic, not bad. Optimal solution length is about 53 moves, 400 million nodes are generated on average solution time is about 50 seconds. When they say current machines, I do not mean current, I mean 10 years ago or so. But what about 24 puzzle, right. So, here 15 puzzle was 6 days, 24 puzzle was 12 billion years, 15 puzzle with Manhattan distance becomes 50 seconds, 6 days to 50 seconds, awesome. But what about 12 billion years to what in 24 puzzle? So, let us talk about Manhattan distance with 24 puzzle. IDA star with Manhattan distance would take about 65,000 years on average. Now, it is great, it is much better than 12 billion years, but you would not want to start a process right now and wait for it to finish someday. Of course, what is the problem? The problem is that the heuristic is good, but not great. It is not modeling a lot of things. For example, let us think about a place where 3 1 needs to go to 1 3. What would Manhattan distance say for tiles 1 and 3? 2 and 2. So, the contribution to Manhattan distance for these 2 tiles would be 4. Can you ever do it in 4? You can never do it in 4. And the reason you can never do it in 4 is because there is a linear conflict. In order to move through their shortest paths, they have to interact, and once they have to interact, one has to go around the other. So, in practice you will need at least 6, you will need at least 6. Why? Because you will move 3, then you will move 1, 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 then you will move 3, or any which way in this order, but you can't get to the other position until you move the first one and go around it. So, if you add some kind of a linear conflict in your heuristic computation, then you will get to a better number and more informed heuristic. So, this was developed in 1991. Given 2 tiles in their goal row, but reversed in position, additional vertical moves can be added to Manhattan distance. Unfortunately, even though it is more informed, it is still not accurate enough to solve the 24 puzzle. So, what do we do? Now, we understand the intuition. The intuition is that look, we were considering these tiles to be completely independent. They could move on top of it. Of course, they should not be allowed to move on top of it. They should only be allowed to move when there is a gap, or at least if there are conflicts and interactions, those interactions should be taken care of. But unfortunately, if we start to take care of all interactions, then we will end up solving the original problem, which will be extremely expensive to solve, and we have not gained anything. So, we have to carve this balance where in the heuristic computation we do something fast, but we still make it an informative heuristic. Many more examples of this show up. For example, if I have this set of red tiles and I want to get to this set of red tiles, the Manhattan distance will say it will take 19 moves, but actually 31 moves are needed. Look how bad sometimes this heuristic computation can get. Similarly, if I have a configuration like this and I have to get to the same configuration, Manhattan distance says 20, but actually 28 are needed, and if I have to go from this configuration to this, Manhattan distance says 17, but actually 27 moves are needed. Now notice we have done something very interesting. I am showing you red tiles, 8 of them or 7 of them, but every other tile is not important. I have just called it white. I do not care for the number. Is this a relaxation? I am making sure that all the interactions of the red tiles are counted, but I just do not care for the final position of the whites. That is also a relaxation of the original problem. So, if I actually solved this problem with completely ignoring what is happening to the whites, the optimal cost that I will get will still be admissible. And that is what is called a pattern database heuristic. Unfortunately, just solving this is going to be expensive. So, we will do this expensive operation once, and all the heuristic values will put in a database. Here is where your database class comes in handy. And then you do an index on top of it, so that your database is now quickly randomly accessible, and now when you actually do search, you ask the database for the heuristic value. You have cached all the heuristic values. You are not doing an on the fly computation. This is called pattern database heuristic. It was developed in 1996. A pattern database is a complete set of such positions with associated number of moves. Example, a 7-tile pattern database like the one that I just showed you for 15 puzzle contains 519 million entries. So, for all these 519 million states, I compute the pattern database, the heuristic once, and in fact, I do it in a batch, so that I can make use of the property that many of these states come together and so on and so forth, and so I do not have to redo the computation, I can just compute it in one pass. So, this would be one such 8-tile pattern, right. So, entire database is computed with one backward search, breadth first search from the goal. By the way, I did not discuss it in the last time, but as we have A star in the forward direction, we can also do A star in the backward direction. And if we can also do A star in the backward direction, I can also do bidirectional A star. And in fact, one of the very recent, like 2-3 years ago, best paper award at a top AI conference was understanding the details of bidirectional A star algorithm. So, believe it or not, A star, which came way back in 60s, there were things to be learnt about that or bidirectional version of that even till the last few years back. It was the best paper award, it was a fundamental contribution in the field of AI. So, if you are interested in bidirectional A star, check that out. And note that here all the non-pattern tiles, the whites are indistinguishable, but I am counting its moves. I am not saying that I will not count your moves, I will count the moves, I just do not care for their final position. Okay? Now, once I have created this pattern database, I can not just create one, but I can create many pattern databases. For example, I convert my 8 puzzle problem into 2 sets of tiles, the red tiles and the blue tiles. And I have one pattern database for the 7 tile red tiles, and I have another pattern database for the 8 blue tiles. And now my pattern database number red says 31 moves are needed, and my pattern database blue says 22 moves are needed. So, what will be the overall admissible heuristic? This is a good question. I gave you 2 heuristics. The first heuristic was counting red tiles carefully, counting blue tiles as if they are indistinguishable, but counting their moves. I gave you the other heuristic H2, which counted blue tiles carefully, counted the red tiles as if they are indistinguishable, but counted its moves. If red says 31 and blue says 22, what is the best admissible heuristic you could come up with? The max. Why? Because if I do the sum, I will be double counting possibly, because I have counted some of the grayed out tiles moves, they may be repeated when they want to get to the correct position. So, therefore, the overall admissible heuristic we can come up with is 31 moves, and people were not happy with this. Intuitively you want to break your problem such that we finally get to the sum, and that is admissible. Can you guess how you would do it with this red tile and blue tile setting? With 31 you add 7. Why would you add 7 to 31? Yeah, but there is interactions. It is possible that in the process of settling with the red tiles, these blue quote unquote indistinguishable tiles came in the right position. Then we would not be able to add anything there. So, right, something else. Yes, Shivam. If we will first settle with the red tiles and then come up with the positions of the blue tiles, but look, at the time of solving red tiles, blue tiles are indistinguishable. We made choices as if they are indistinguishable. In fact, if we knew their numbers, the state space will become so large that we will not be able to solve this, right. We have divided it so that we can solve the state space. There is another trick. Yes, what is your name? Yes, Jay. While moving the red tiles, don't count blue tiles at all. Only count the moves of the red tiles. Allow you to make as many blue tile moves as you want, just don't count it. So, individually you will come up with a lower heuristic value, but then it will be additive because you are never doing double counting. You are never even counting the blue tile moves. So, this is what is called additive pattern databases. We can only count moves of pattern tiles, ignoring the non-pattern moves. And if no tile belongs to more than one pattern, like red and blue are separate, then we can add their heuristic values. In fact, Manhattan distance is a special case of this, where each pattern contains a single tile, everything else is grayed out. Yeah, because you are not counting the others moves. Good. So, you can divide it in any which way. You can say these are my red, these are my blue, or whatever. In this case, the 7 tile database will contain 58 million entries, and the 8 tile database will contain 519 million entries. And for example, if the blue database says that the 20 moves are needed to solve red tiles and 25 moves are needed to solve blue tiles, then you can come up with a better heuristic 45, which is admissible. So, now just the final slide to show you that it works. This gives you 2000x speed up versus Manhattan distance. IDA star with the 2 databases shown previously solved 15 puzzles optimally in 30 milliseconds. Maybe it is not counting heuristic computation time. So, that is not fair, but still it is fast. But more interestingly, what happens in 24 puzzle, where we would have needed 65,000 years earlier. It can solve a random instance in 2 days. 2 days is still not very good, but at least it is much better than 65,000 years. And also we are talking about 15-year-old papers. So, probably now we can solve it in a few seconds. For 24 puzzle, they use 4 databases, additive, using this 6 tile, this 6 tile, this 5 tile, and this this 6 tile and this 6 tile. So, 4 6 tile databases, and that sort of gives us the final result that we were looking for. So, let me summarize. So, we have been discussing this whole idea of search algorithms, and we have now come to a nice landmark point where we have studied a lot of search algorithms which are going from the start state and developing a tree and sort of maintaining part of the tree in my memory or visiting it and backtracking it and things like that. there is memory implications, there are time implications, whether you maintain the frontier or you do depth first. We have also figured out how to use additional heuristic function, additional information to do things faster, and we have done several examples to think about how quickly they can solve some problems if you have a good heuristic. We have discussed how to compute good heuristics, at least admissible heuristics, you require domain relaxations, and then these relaxations can sometimes become large. So, sometimes you want to do them in a batch, compute all heuristics and then put them in a database, and sometimes state space is too large, you cannot do this. So, you break the state space into multiple subparts, compute heuristics on top of them, put it in multiple databases and max or add them. These are called pattern databases. So, this is our story up to now, and in the next segment, in the next class starting tomorrow, we will talk about local search, a very different, but in some ways in my opinion more practical, even more practical than these algorithms, a different mechanism for doing search and solving problems. We will stop here.